And now we're recording. Okay, so I'm going to pick up where we left off. Last class we were talking about the substitution income effect, and I had put up an example on the board. This was from the book, but as I'm looking at the book right now, I see that I did not put the income in there. The income level should be 100, as you probably have figured out by now. But since we're not constrained by time, this is a video, I'm going to go ahead and work through this just for review, and then I'll show you how to decompose substitution income effects when a price changes. So first, let's solve this. You should be able to tell by now what kind of shape that indifference curve is. If you can't, you can solve for x2 and determine for yourself that it should cross the axes but be bowed in. I'm not going to derive that here. You should be able to do that by now. But if you're uncertain as to what method we should use to solve the consumer's problem or the UMP, you can first solve for the indifference curve, and it should have intercepts of u on both axes. And so since this is bowed in, what we're going to do is look for a tangency. We're going to look for a tangent point to find our solution, but we're going to be careful because since it touches here at the axis, we might be worried that it crosses actually in the second or fourth quadrants. But we'll know because we'll get a negative number for one of the goods. So we're going to go ahead and use the Lagrange method to solve for our optimal bundle. So the Lagrange function here will be the objective function minus lambda times the constraint. So using the points I gave, the prices are both $1, the income's 100. That'll be x1 plus x2 minus 100. Now I'm going to solve for the first order conditions here for x1, x2, and lambda. Oh, made a mistake already. We got to bring down the exponent here. Right, we got to do the chain rule. So what I'm going to do is I'm going to write all this stuff in here with a little dot because I know it's going to cancel. So this parentheses with a dot just means there's stuff in here. And I know when I write this again, it's the same stuff. So that'll save us some time. And then we should have a negative lambda, and that's all going to be set equal to 0. Call this, I like to use green, equation 1. It's our first order condition. And we'll have a symmetric first order condition for x2. Call that equation 2. And as always, we will get back our constraint when we take the derivative with respect to lambda. So here are 3 first order conditions. I can see that the 2's and 1/2 are going to cancel out. And if we use our trick to divide equation 1 by 2, after we put lambda on the right-hand side, you can see that the stuff inside the parentheses is going to cancel. We're just going to be left with this x1 and 2. Since lambda is on the right-hand side over here, and we divide 1 by 2, that's just going to give us the number 1. And so combining those two, we will get our tangency condition. But since this camera doesn't go to the other boards, I'm going to have to erase this and draw over it. So hopefully you have that copied down. Or you can just replay the video. Or maybe I could just use this space. I'm going to do that. Okay, so taking, let's do 1 divided by 2. What we'll end up with is x2 over x1. I'm going to go ahead and flip them because they have negative exponents. So I'm going to flip their order so that I can write to the positive 1/2 equals 1. Because again, on the right side, we'll have lambda divided by lambda. That's 1. I can square both sides. And if I do that, and if I take both sides squared, 1 remains 1. But this side will get rid of its exponent. When we take 1/2 to the second power, it becomes just 1. And so after doing that, left with x2 over x1, which can be rearranged to say x2 equals x1. And this is our tangency condition. I think we've gotten this far before, or I think we discussed just in words without solving anything, that if you look at the original utility function that I had to erase, x1 and x2 entered it in the same way. So the consumer didn't prefer one over the other if prices were the same, which they were here. So it should be the case that in equilibrium, when the consumer is being optimal, he or she will consume the same amount of x1 and 2 because the consumer likes them the same and they cost the same. And given the shape of the indifference curve that we drew up here, you know the consumer will probably want to have some of both. So this makes sense. We should expect this. So now our system of equations is really just 4 and 3 because 4 is 1 and 2 combined. So what we'll do now is take 4 and put it into 3. And in doing so, we will have combined all 3 of these equations into 1. And that one equation should give us an answer. So doing so, I'm going to put everything in terms of, let's say, x1. We have x1 plus x2, which is the same as x1, equals 100. And that gives us x1 equals 50. I couldn't decide if I wanted to call it something Walrasian or Marshallian, but we don't put a subscript on it. We just leave it as is. So this is our Walrasian demand. If x1 is 50, according to equation 4, x2 is also 50. Maybe I should call those XPI, because it's based on price and income, where price is 1, and income is 100. You can write it that way if you like. Okay, so let's graph what we have here. So I have found a point here, 50-50, that tells us the consumer's optimal consumption bundle, given an income of 100. So it should have intercept of 100, 100. Because at most we can afford 100x1 or 100x2. Now, let's change the price. Let me follow the book here of, I think we changed one price to 4. Price 2, let's change price 2 to 4. So if we go back, if you go back to look at the Lagrange function that we optimized, the only thing that will change, well, it might change some more. Let me write it down. I'll just write it down. Tell you what, I'll write in red all the things that change. And everything else that will be in black here will be identical to the last problem. So all we changed is the price of good 2. So there's going to be a 4 in there now. When I take the derivatives, the first one should be the same. But the second one is going to have a 4 in there. Forgot to put it in red. So this is the only thing really that changes in the second first order condition. And of course, when we take the last one, the 4 is still going to be there as well. And I don't know why I put parentheses around there. That's not necessary. But in any case, this is actually going to change our tangency condition. The left will be the same, but on the right we'll have 1 over 4. So let's see what happens there. I want to leave this up here, the graph. So I'm going to erase this and combine these two into 1. But we're doing the same process we did last time. So what those two equations will become is x2 over x1 to the 1/2, same as before, equals 1/4. So I guess I should say this is different. So when we square them this time, if I square both sides, now we're going to get 1/16 over here. So what we'll have is x2 equals 1/16 of x1. Or if you want, you don't like fractions, you can write x1 equals 16 times x2. Let's just do that. Say x1 equals 16x2. Which means when the consumer is optimizing, he's going to consume 16 times the amount of x2. His x1 consumption will be 16 times the amount that he consumes of x2. That's what I meant to say. So let's put that in now to the third equation, and we will have combined all 3 pieces of information into 1, and the system will tell us what x1 must be when all 3 pieces of information are true. So instead of x1, I'm going to put in 16x2, and we'll be left with 20x2 equals 100, or x2 equals 5, and if x2 is 5, then x1 will be 16 times 5, which is 80. I'm sorry, x1. Yeah, x1 will be 80. So what happens here is we increase the price of x2 to $4. So with an income of 100, we can now only afford 25 of those. Well, that's a big increase. And so our budget line rotated in this manner. And so now we're only consuming 5x2 and 80x1. So we should be close to here. If 80 is there, maybe this is 5. And then we must be somewhere like this. So tell you what, I'm going to call this No, I don't want to label those. I'm not going to label them right now. This is the point we're actually at. So both of these points we solve for are Woolradian demand or Marshallian demand, however you want to say it. So our consumer consumed more X1, less X2, which makes sense. X2 became more expensive and nothing else changed. But there's actually two things going on here. One is the substitution effect. The consumer is going to substitute to consume more X1 because it's relatively cheaper versus X2 now. And two, the consumer is going to want to consume less of both goods because he feels poor. When price goes up to $4 for X2, you now can't afford as much as you used to purchase. So in real terms, you actually are poorer than before. So you'll want to consume less of both goods because you have less real income, and that's called the income effect. That is you consuming less overall of everything because you have less real income. So we can separate these two by solving for what the consumer would have purchased if you allowed prices to change. So we're still on this new budget line, but you compensated them. You gave them enough money so that they could attain the same level of happiness they did before the price change. So think about that. If I just give you money, that's shifting out this budget line. So I'm going to draw this as a dotted budget line because it's not real. This didn't happen. We're not observing it. This is a hypothetical what if. What if you could afford that level of happiness? Now, we're not saying you could afford the same bundle that you purchased, because if you look here, you can't afford it. We're saying, what if you can afford that level of happiness, right? Because right here, this is a point that is on that indifference curve and on that new budget line, a hypothetical one that you can afford, and it'll bring you back to the same level of happiness you originally had. So how do we solve for this point? Well, there's two ways. One, we can use two pieces of information. One, I know that the indifference curve is tangent to this hypothetical budget line. That's one piece of information. I could write that equation. And two, I know that we're on this level of utility. Now, unfortunately, I didn't solve for that level of utility, so I don't know what to plug in there. But if you did solve for this level of utility, you could have that be another equation. You could say this expression here equals that number, whatever that level is. You could take those two pieces of information, that's two equations, you could solve for X1 and X2. Because at that point, you have two equations and two unknowns. I didn't solve for that utility level, so instead, I will show you, I guess, another way to do this, which is we can find this point by solving the expenditure minimization problem. That's a new thing we recently learned. So we could constrain ourselves to say, hey, what if I force my consumer to have this level of utility? Actually, we would need to know the level in that case too. So in either case, we need to solve for it. I'm going to come back to this. Let's just figure out what utility was in the last situation. So in the first point, we had a consumption of 50-50. So I'm just going to plug that in. Let's see what utility was. Ooh, should I use calculator? We have 2 times 50 to the 1/2, all squared. So if I distribute that squared to both terms here, we'll get 4 times 50, or 200. There we go. So now I know this utility is 200. Okay. So we can solve this in one of two methods. The first, like I said, I could use the equation utility equals 200 and the tangency here, two equations, solve for the two unknowns, x1 and x2. Or we could solve the expenditure minimization problem, constraining our consumer to have a utility of 200 and giving the new price $4 and $1, which will give us this slope, and then say, what's the least I could spend? We're going to get this answer. So let's go ahead and do that way, since that's a relatively new thing we learned. We could review that. So what we're going to do is say, what is the least I could spend? Minimize expenditure. I'll write that down. We want to minimize choosing X. And we'll choose lambda 2. Does lambda have to be positive? No, it does not. So let's say this. Let's just not say where they're coming from. We know what they are. We're going to minimize X and, no, wait. We're choosing X and lambda. Yes. Sorry, guys. We're choosing X and lambda to minimize P dot X, subject to the constraint that this utility function is at least as big as 200, or at least as great as 200. Gives us the utility of 200 or more. Now we can make an argument that since more is better for this utility function, you'll never want to not spend all your money. So if you always want to spend all your money, you will never not be on the budget line. And you will never want to purchase more than you have to get this utility level. Because there's many points on this indifference curve that'll give us this level of utility. There's points beyond the curve that'll give us a higher level of utility. But our goal here is not to maximize utility. Our goal in this problem is to spend as little as possible and get at least this amount. So since more is better and prices are positive, being happier at one of these points is going to cost you more. But our goal here is to spend as little as possible, so we don't want to do that. Therefore, we can make a logical argument that this will hold with equality when our consumer is being optimal. Since that's the case, the solution to this problem is the same as the solution to the problem that says you have to be at least as happy as 200. Because you'll get the same solution no matter which one we solve. So since we can write it this way with an equality constraint, we can use the Lagrange method again. The difference here is the objective function is now the budget line. That's what we're trying to minimize. So our objective is price 1 times x1 plus price 2, which is 4, x2, minus lambda times our constraint. But now our constraint looks like what our objective used to be. So it's going to be very familiar, but it'll operate slightly different when we plug things back into the constraint. Wait, I need one more. There we go. Now it's complete. So let's go ahead and take the first order conditions. And I'm making use of the dot again to mean all that stuff. Save us some space and time. Oh, we need a 4 here, not a 1. Price is 4 for good 2, so that'll be the only thing that's not symmetric. Okay. Now we have our new 3 first order conditions. So we can combine 1 and 2 the same way we did last time. And actually, looking at this, we're going to get the same equation, right? If you look at this, the lambda here is attached to this equation now, which is utility. But when we take this to the right side and divide them, it's going to cancel out. We'll have 1/4 on the left and x2 over x1 to the 1/2 on the right. This is the same condition because these two equations are just giving us the tangency condition. And the tangency condition is the same in both of these problems. In both problems, we're saying the slope of the indifference curve is equal to the slope where prices are 1 and 4, right? That's the same here and here. So this is actually going to give us the exact same thing. When you combine these two into our fourth equation, we're going to get 1/4 equals x2 over x1 to the 1/2. And once I square both sides and rearrange, we will once again get x1 equals 16 times x2. So that's the same as before. What's different now is when we plug that into the constraint, our constraint is not that linear equation anymore. It's the utility function. So let's plug 4 into 3 and see what happens. I'm going to have to erase this up here for space and do it up here. All right, so again, I'm just plugging this into here, and then we'll have that one statement that combines all three, and we should get an answer for x2. Okay. So instead of x1, I'm writing 16x2. Now be careful here, because we have x1 to the 1/2. So we want to write everything to the 1/2, all of this. Plus x2 to the 1/2, all squared, and I'm going to move negative 200 over here so that we have no more negatives. Okay, well obviously we want to take the square root of both sides to get rid of that squared term. That's the same as saying take everything to the 1/2. Ooh, what does that do here? That gives us not a nice number. We can look at this as 2 times 100. So I take the square root of that, I got square root 2 times 10. I think that's as nice as it can get. So let's see what happens here. This becomes well, maybe I'll just leave it 200 to the 1/2. Maybe something nice happens later. These two will cancel out. So I can get rid of that. Okay. Well, I can add those two together, right? Because they're like terms. But before I do that, let's be careful. Make sure I plug this into both terms here. This is where I see students make the most common mistake. You will forget to do this step. But if you remember, what you'll get is 4x2 to the 1/2 plus x2 to the 1/2. And it doesn't look like that this is going to change anymore. Well, we'll see. This is 5x2 to the 1/2. Now I can divide both sides by 5, but that's not going to fix our square root problem. So maybe now's a good time to just say we can write this as 2 to the 1/2 times 10 to the 1/2. Or I'm sorry, 100 to the 1/2, right? Because 200 is 2 times 100, but 100 to the 1/2 is actually just 10. So when we divide by 5, again, you don't necessarily have to do this. I'm just trying to make it look nicer. When I divide by 5, what I'm going to get is 2 times 2 to the 1/2. Oh, maybe this does work, which equals 2 to the 3/2. Okay. That's not so bad. Of course, I don't know what it means to consume 2 to the 3 halves of an item, of a good. Oh, we still need to square both sides because x is to the 1/2. Ah, here we go. It's going to end up nice. Remember this equation right here because I have to erase it. All right, so when I square both sides now, I get x2 equals 2 to the 3rd, and that is going to be a nice number. That's going to be 8, right? Or, yeah, it should be 8. And so plugging this back into our equation 4, we get x1 is 16 times that amount. 16 times 8 is 128, I hope. Should probably check that. The only kind of mistake I usually make is simple arithmetic. I'm right, good. Okay, so what we solved for here is this new point. This is getting messy, so I'm going to rewrite some of this. 50, this was our 80. Now we have 128, and x2 was 8. So I know that's getting kind of smashed in there. I'll draw bigger graphs next time. Or you know what? We really want to see all this in detail. So let me redraw this much bigger. So what this is saying, I'm going to label all these points. Let's call this original purchase bundle A. Let's call this second purchase bundle C. And I'm going to call this 128.8 bundle B. So sometimes this is called the decomposition bundle because it helps us decompose our change in demand from A to C, which is what actually happened. We went from consuming at A to C. It helps us decompose this into the substitution effect, which is A to B, and the income effect, which is B to C. And the reason why it does this is because if you look at A and B, we have the same level of happiness. The only thing that changed is the prices. So it's like saying, well, what if you could afford to remain as happy as you were before, but the prices changed? So you can still afford your same level of happiness, but good 2 is still 4 times as expensive now. You would substitute x1 for x2 anyway, even if you could afford the same level of happiness because it's now relatively more expensive. So you didn't like B 4 times as much after that change. So obviously you're still going to rearrange your consumption bundle. So going from A to B, all that's changing is the price ratio, right? The slope of the budget line. So in that case, any change from A to B, say going from 50 to, I didn't label it 120, oh, I did right here, 128, that is the substitution effect. For x1. So for x1, the substitution effect is we consumed, what is that, 78? 78 more units of x1. So that's the substitution effect because of the price change, but nothing else, right? We're pretending like you don't feel poor because we gave you the money back. That's what this hypothetical budget line represents. What if I shifted your budget line out? I compensated you for that change in price. That's what we call this, the compensated or Hicksian demands, right? If you want, we can put H's on there. We probably should to keep them separate. So what we solved for here with the expenditure minimization problem was the Hicksian demand or compensated demand, because it's what you would demand if you were compensated, thus shifting your budget line out for that change in price. And if you were compensated in such a manner, you would buy 78 more x1. That's the substitution effect because that is how you would substitute when prices change without an income effect present. We got rid of the income effect by giving you money. For x2, let's see, we went from 50 to 8. So the change was negative 42. So this means that the substitution effect on X2 was you consumed 42 units less because it's relatively more expensive relative to X1. Okay, now what does it mean when we go from B, the bundle that we don't see? Again, this is hypothetical. You don't actually see this in reality. From B to C, what is the difference? The difference there graphically is it's as if I just took away income, right? This is representing the loss in income you feel, a loss in real income from that price change. So the change from bundle B to C is your income effect. So at C, we are consuming, let's see, 80 X1. And at B, we were consuming 128. So that's a difference of negative 48. That's X1. For X2, we were consuming 8, and now we're consuming 5. So that's a change of negative 3. What this means is that the income effect is that you consume less of both goods. And that makes sense because the income effect is you feel poorer when one of the goods becomes more expensive. So obviously, you're going to consume less of both. Even though good one's price did not change, the income effect still says you're wanting to consume less because you feel poor. Now, overall, what happened to X1? Originally, it was 50, and after the substitution effect, it went up to 128. After the income effect, it went down to 80. So overall, you still consumed more X1. That's not always going to be the case. In Cobb-Douglas functions, I think I mentioned before, the substitution income effect will cancel out and you'll go back to 50. But here we're looking at a CES function, a general CES function that's not Cobb-Douglas. So this is possible. For X2, the substitution effect brought us down. We label 8 here. If 8's maybe it'd say here. The substitution effect wanted our consumer to substitute away from X2, and the income effect made the consumer feel poor, so he consumed less for that reason as well. So both effects there were causing the consumer to consume less. So obviously overall, consume less X2. But again, the main point here is that we don't see this bundle B. The actual change is our consumer went from A to C, but he changed his consumption for 2 reasons. One, the change in price will cause him to substitute towards the relatively cheaper one. And 2, the income effect is going to say, well, I feel poor now, so I'm going to consume less of both. So if we trace those movements, see if purple is going to show up, find out. So again, A to B is saying we're moving along this line and substituting in this fashion, right? Less 2, more 1. Income effect is saying I feel poor, so less of both, right? We're going down direction for both. Maybe that's getting kind of crowded, but you get the idea.